this lecture about refrigeration cycles. Before start the refrigeration cycles, we will study some basic thermodynamic cycle, that is heat engine, heat pump, refrigerating machine. Say this dotted line is representing the ambient temperature TA. First of all, heat engine. What is heat engine? As we know that heat engine is the device which will produce some work by expense of heat. Say this is the source of T1 temperature and this is the sink of T2 temperature. Between these two there is a heat engine. Say Q1 amount of heat will supply from source at T1 temperature and it will develop WE amount of work and Q2 amount of heat will rejecting to the sink at temperature T2, and we can say T2 is greater than equal to TA. Now come to the heat pump. What is heat pump? Heat pump is the device which will maintain a certain space temperature above the atmospheric temperature. Say this is the heated space. Of temperature Tk, which is greater than that Ta, and this is the source temperature T naught. You can say source, that is because from here the heat will extract it, and this is the heat pump. Say Q1 amount of heat will extracted from the lower temperature body and Q2 amount of heat will supply to the heated space, and that is why WH amount of work we have to invest to the system, and for that case T naught is less than equal to TA. And what is refrigerating machine? This is nothing but a machine which will maintain the temperature of a particular space less than that of atmospheric temperature. Say this is the cold space. Of temperature T naught, which is less than TA, and this is the, for that case, sink, suppose Tk. So, this is the device which is called refrigerator. Say Q1 amount of heat will extracted from this cold space to maintain the T naught temperature, which is less than that of T A, and that is why we have to invest W R, and the device will rejecting heat to the sink of T2. For that case, Tk is greater than equal to Ta. Now, to find out the performance of the heat engine, as we know, that has been defined by the efficiency. Efficiency of the heat engine is equal to work output divided by work input. So, what is the work output? That is WE. What is the heat input or work input? That is Q1. We can calculate this WE is equal to Q1 minus Q2 divided by Q1. For heat pump, we have to find out the performance of the heat pump by means of COP, coefficient of performance. So, coefficient of performance of heat pump, that will be is equal to desired effect divided by work input. Now, what is desired effect? Desired effect, for that particular case, we have to maintain the temperature of this particular space Tk, which is greater than that of atmospheric temperature, and that is why we have to supply the heat at the rate of Q2, because we assume that some heat will utilize for some purpose or leakage from the system at the same rate, that is Q2. So, for that particular case heat pump, the desired effect is what? Q2. And what is the work input? Work input is Q2 minus Q1, and that can be written from the basic relation Tk divided by Tk minus T naught for that particular case, because Q2 related temperature is Tk and Q1 related temperature is T naught. And for that refrigerator or refrigerating machine, what will be the COP? The COP of refrigerator will be similarly desired effect divided by work input. For that particular case, desired effect is nothing but Q1, because we have to maintain this T naught temperature, which is less than that of atmospheric temperature. That is why we have to extract the heat at the rate of Q1. So, that is for that case Q1 is the desired effect and work input is Q2 minus Q1. Similarly, we can write this in terms of temperature T naught divided by Tk minus T naught. So, that is the basic concept of heat engine, heat pump and refrigerator. Now, another cycle we will study before starting the refrigerating cycle, which is most efficient. So, the best refrigeration cycle, that is reverse Carnot cycle. We will study that. Reverse Carnot cycle. What is reverse Carnot cycle? Sadi Carnot in 1824 proposed a reversible heat engine cycle as a measure of maximum possible conversion of heat into work. A reversed Carnot cycle can therefore be employed as a reversible refrigeration cycle, which would be a measure of maximum possible COP of the refrigerating machine operating between two temperature, that is Tk. We can say this is the Tk temperature and Tk of heat rejection, for heat rejection, and T naught is refrigeration. So, this is T naught. So, as we know that the basic structure of TS diagram for Carnot cycle is just like that. If we start from the compression process, say this is the one point. So, 1 to 2 process is adiabatic compression or isentropic compression. So, we can say 1 to 2 is isentropic compression, and for that case definitely S1 is equal to S2, and after that isothermal heat rejection. So, that has been executed in condenser session. So, isentropic heat rejection. So, we can say this is the Q2 and 2 to, so 2 to 3 processes isothermal heat rejection. So, 2 to 3 processes isothermal heat rejection. Clear? And after that 3 to 4 process, 3 to 4 process is what? Isentropic expansion. And for that case S3 is equal to S4, and after that 4 to 1 process is isothermal heat addition. Clear? So, by amount of how much? Q1. And what is the basic working principle within this cycle? I will elaborate in next slide. So, this is the Carnot cycle, reverse Carnot cycle. Is that clear? Now, this reverse Carnot cycle may be used for heating purpose or cooling purpose. First of all, what is the Q1? Q1 is what? Q1 is definitely area under the 4 and 1, which is this area. That means T naught into del S. What is del S? Del S is nothing but this one. This one is del S. You can say del S is nothing but S3 minus S1 or S1 minus S3 or S2 minus S4. This is the del S. And what is Q2? Q2 is equal to similarly Tk into del S. And what is W net? W net will be definitely. So, for that case, for 1 to 2 compression, we have to supply some work WC. For expansion process, we will get some work WE. So, W net will be WC minus WE. That can be calculated by Q2 minus Q1. Clear? So, what will be the COP for cooling purpose if we use this device? So, for cooling, COP, what will be? Desired effect divided by work input. For cooling purpose, we will consider this Q1 is the desired effect, because from this space the heat is extracted by the working fluid and we are maintaining the temperature of this particular space below the atmospheric temperature. So, what will be COP for that device if we use as a cooling purpose? That is, desired effect is Q1 divided by work input is Q2 minus Q1. So, Q1 related temperature T naught and that will be Tk minus T naught. Clear? When the T naught is 0, then what will be the COP? COP for cooling will be 0. When the T naught is equal to Tk, then T naught is Tk, then COP for cooling purpose is infinite. So, we can say if we use this reverse Carnot cycle for cooling purpose, the COP will vary between 0 to infinite. Now, for heating purpose, what will be the COP? Similar way for heating purpose. So, for heating purpose, desired effect will be this space. That means, for that particular space we are supplying Q2 amount of heat to maintain the temperature above the atmospheric temperature. So for that particular case, COP of this device for heating purpose, that will be desired effect is Q2 divided by work input is same, Q2 minus Q1, that can be written as Tk by Tk minus T naught. And when the Tk becomes 0, then what? Then COP for heating purpose is what? 0. When the T naught becomes 0, then COP will be for heating purpose will be what? 1. So we can say if we use the reverse Carnot cycle, then COP will vary between 0 to 1. This is a important information. This is important. And also we can say the COP of this device is function of temperature only, not depends on the working fluid. Clear? Now we will proceed for another topic, that is vapor compression refrigeration cycle, which is very important. Now what is the vapor compression refrigeration cycle? In vapor compression refrigeration cycle, 4 basic units are there. What? First one is if we consider, first one is evaporator. This is evaporator. Then compressor. Then condenser. Then expansion device. We can get from the last slide, we can get some work output due to expansion if we use some expansion device which will develop some work. But if we use the expansion device for having this minimum work, we have to that process is not so economical. So that is why to sacrifice this WE, we will use another device which will play the same role as we required, that is the expansion device, that is capillary tube, which will same, the pressure will drop as well as temperature will drop, but work remains same, the change of work is 0. So for that case, that is expansion device, expansion expansion device, or for particular case capillary, CT for capillary tube. Now this line will represent some reference line, because we know that simple vapor compression refrigeration cycle will work between 2 pressure line. One is high pressure or discharge pressure. So above this line, this is high pressure, high or discharge pressure, and below this line is low pressure or suction pressure. Clear? And these 2 pressure line is representing here in HS diagram, TS diagram and also PV diagram. This red line representing the high pressure line or discharge pressure. So we can say this is P discharge, and this green line will represent P suction or low pressure. Similarly here P discharge, P suction. For that case, P discharge, P suction. Clear? Now, if we start from here, that is before evaporator, sorry, after evaporator, before compressor, say this is point 1. If we consider after evaporator, the condition of the working fluid, that is refrigerant, is dry saturated vapor, that is this point, say 1, then it will say this is dry compression. If that condition of the working fluid is wet, say that is within this vapor dome, that may be here, that may be here, is called wet compression. So, we will consider for that particular case dry compression. So, this is 1, and 1 to 2 process, that means if we say this is the 2 after compression. So, 1 to 2 process is adiabatic compression, or you can say isentropic, reversible adiabatic compression or isentropic compression. Here we have to supply some work, that is WC, and if we represent this same on this HS, TS and PV diagram, that will be just like that. 1 to 2, some work on the system, 1 to 2, some work on the system, WC, 1 to 2, some work on the system, WC, and after that, due to the compression, the temperature and pressure will increase, and for that high pressure, the boiling point of working fluid will increase, and the temperature of the working fluid will be greater than that of atmospheric temperature, and that is why due to the temperature difference, there will be heat transfer from the condenser, and heat will transfer until or unless, for that particular case, say that becomes saturated liquid. That means, here say due to the temperature difference, Q2 amount of heat will reject from the condenser to the atmosphere, that is called sink, and 2 to 3 process, that is isobaric through the constant pressure line heat rejection. So, 2 to 3 process is heat rejection process. So, how much amount? Q2, and for that particular case, we assume the working fluid becomes saturated liquid and heat will reject, and suppose for TS diagram, that will be 2 to 3 process. How much amount heat? Q2 amount of heat will reject from the system, 2 to 3 process. How much heat? Q2 amount, and after that, that will passing through the capillary tube, which is nothing but an expansion device, where the pressure will drop and temperature will drop, but enthalpy remains constant, as we know the working principle of capillary tube, and this is suppose 3 to 4 process. So, for that case 3 to 4 process, enthalpy constant, enthalpy remains constant. So, suppose this is the 3 to 4 process, where enthalpy remains constant. So, for that case H is equal to constant. Clear? So, for that same, if we draw in TS diagram, that will be just like that, 3 to 4, H is equal to constant. For that 3 to 4, H is equal to constant. we use dotted line because this throttling process is irreversible process. So, in this cycle all the process is reversible except this 3 to 4 process, that is throttling process. After throttling the temperature will drop. You can see actually this throttling device is responsible for cooling effect for that case or for that cycle, and due to the pressure drop the boiling point of working fluid will drop, and due to the low boiling point whatever the air coming from the cold space, there will be a temperature difference between the working fluid as well as the working fluid and air which is coming from the cold space. Say, let me make you understand, let me say this is the cold space. Suppose from here the air is coming and return back to the cold space. Say, whatever the working fluid we are using, say the boiling point of the working fluid say minus 10 degree Celsius normally, and due to the pressure drop say now boiling point becomes minus 15 degree Celsius. But whatever the cold space air just coming into the evaporator, say the temperature is minus 1 degree Celsius. So, definitely minus 1 degree Celsius is greater than minus 15 degree Celsius, as well as whatever the temperature after expansion, the temperature is also less than that of minus 1 degree Celsius. For that particular case, I use this nothing but as an example. So, due to this temperature difference, the working fluid will take heat from the air which is passing around this, which is just coming from the cold space, and it becomes evaporated. So, that is the basic working principle of evaporator. And say how much amount of heat? Say Q1 amount of heat will take from the cold space. Clear? So, this process we can represent in HS diagram. 4 to 1 is heat addition process, isobaric heat addition process. 4 to 1 in TS diagram by Q1 heat addition, PV diagram Q1, this is the process. So, this is a particular, this is the basic working principle of vapor compression refrigeration cycle, and after evaporator then again it will come to the compressor, condenser, expansion device, that is capillary tube for that particular case, and evaporator, and cycle is just like that. So, that is the vapor compression refrigeration cycle's working principle. Now, if we have to find out the performance of that particular cycle, vapor compression refrigeration cycle, then we can easily calculate. How? Just if we get the energy value at 1, 2, 3, 4, then very easily we can calculate this. So, COP of that particular case refrigerating cycle is what? Desired effect divided by work input. What is desired effect? For that particular case, Q1 is desired effect because we have to extract the heat at the rate of Q1 if we want to maintain the space temperature, say Tc, which is less than that of atmospheric temperature, which is less than that of T atmosphere temperature. So, desired effect is Q1 and divided by work input is what? Wc. We can calculate this Wc, that is Wc. How can we calculate? Q1 is nothing but what? H1 minus H4. So, mass flow rate of working fluid into H1 minus H4 divided by what? mass flow rate of working fluid into H2 minus H1. This is a very simple process. Now, we can see that from this HS, TS and PV diagram, we can get the various idea or of this particular cycle, that means vapor compression cycle. But in refrigeration cycle or refrigeration practice, enthalpy is the most sought after property, and the diagram in pH coordinate is found to be the most convenient. The constant property lines in pH diagram we will see next. So, this is the pH diagram, which is very important diagram if we are going for refrigeration cycle. This is the pH diagram. Let me make you understand the pH diagram. In y axis it will represent P, pressure, and x axis it will represent enthalpy, specific enthalpy, and this is the vapor dome. This color will represent the saturated liquid line, and this color will represent dry saturated vapor line, and this is, you know, this is the critical point, and this line will represent, this line will represent or is representing the dryness fraction line, constant dryness fraction line. So, we can say this is x constant, x constant, x constant. So, we can say this color, this line, particularly this line will represent what? X is equal to 0, and this line will represent what? X is equal to 1, and this red line, that means here vertical, then horizontal, then going downward direction. So, this line will represent constant temperature line. So, T is equal to constant, you can say T is equal to constant, T is equal to constant. So, constant temperature line, clear. Now, this green color, inclined green color will represent the S constant, that means this is isentropic line, entropy remains constant, S is equal to constant, S is equal to constant, and this purple color will represent specific volume, constant specific volume, volume is equal to constant, volume is equal to constant, clear. Now, that becomes more interesting for that particular case if we draw the same process in this HS diagram. 1 to 2 process is what? 1 to 2 process is adiabatic compression, 2 to 3 is isobaric heat rejection in condenser, 3 to 4 is throttling process, that is expansion process. During this enthalpy remains constant, and 4 to 1 process is isobaric heat addition. So, this is isobaric heat addition, and 1 to 2 just like that. So, if we represent this same process in HS diagram, a pH diagram, then what will be? So, say this is P and this is H, say this is the diagram. So, two pressure lines are there, as we know, two pressure lines are there, say one is suction pressure, another is discharge pressure, say 1 to 2 process. So, 1 to 2 process, 1 to 2 process. So, isentropic. So, as we know, isentropic is line is just like that, inclined line. So, here we can say this is isentropic process, inclined. So, 1 to 2 WC, 2 to 3, that is isobaric heat rejection in where? Condenser by Q2. So, 2 to 3, and 3 to 4 constant enthalpy process, throttling process. Here also we have to use dotted line because this is irreversible process. 3 to 4, H constant, and 4 to 1 is evaporator section heat addition by Q1. So, this is the process which has been discussed earlier in with help of HS, TS and PV diagram. So, from here if for a particular case, if we get the different cardial point temperature as well as suction pressure and discharge pressure, then very easily we can find out this 1, 2, 3, 4 point, and help of this pH diagram we can get for a particular refrigerant pH diagram, we can get the COP of the particular case. That will be very simple, which has been shown earlier, mass flow rate of working fluid into H1 minus H4 divided by mass flow rate of working fluid into H2 minus H1, clear. So, this is the COP. So, I hope this lecture will help you to understand the basic concept of refrigeration cycle. Next lecture, I will describe more important part of this same. Thank you.